diesel particulate filter operation in a heavy-duty diesel after-treatment system. Inside the modern heavy-duty diesel engine, pistons rise and fall rapidly within the engine cylinders. Fresh air enters the combustion chamber and mixes with the fuel that is injected. This mixture is compressed, which triggers ignition. Ignition causes expansion that drives the piston back down, generating the energy needed to turn the crankshaft. The byproducts of combustion include solid particulate matter, which is a combination of partially burned fuel and lubricant, which will enter the combustion chamber. Below the cylinder, the engine oil sump is filled with oil, which is circulated through the engine. The oil is sprayed or splashed onto the cylinder walls to lubricate components, reduce friction, remove contaminants, and dissipate heat. Inside the combustion cylinder, the engine oil lubricates the metal-to-metal sliding surfaces between the piston rings and the cylinder liner, as well as removes any post-combustion contaminants like soot. During this process, a majority of the oil returns to the sump. However, a small amount of the oil remains in the upper cylinder post-combustion. At this point, the lubricant hasn't burned. It is mainly clinging onto the particulate matter and getting ready to ride into the exhaust. The exhaust gas recirculation system, or EGR, sends a portion of the exhaust through an exhaust cooler and then back through the intake manifold to help minimize nitrogen oxides, or NOx, in emissions. Not all exhaust is recirculated through the EGR. The remaining exhaust runs through the after-treatment system. Fuel is also used to elevate the temperature of the exhaust system by way of a post-combustion injection into the exhaust stream as it exits the cylinder, or by a fuel doser valve, which is located prior to the after-treatment system. This fuel doser is also known as the seventh injector. Any fuel injected into the exhaust stream negatively impacts fuel economy because it is used to heat the after-treatment system rather than produce power to the crankshaft. This process of elevating the exhaust temperature enables the DPF system to operate properly in removing the particulates, a process known as regeneration. The diesel oxidation catalyst, or DOC, functions to oxidize hydrocarbons and generate the exotherm resulting from the injected fuel. The burning of the particulate matter happens in the DPF, provided the temperature conditions are favorable. When conditions are favorable, exhaust temperatures are hot enough to burn away most of the particulate matter from the fuel and lubricant that is trapped in the DPF. The Selective Catalytic Reduction System, or SCR, also reduces NOx emissions. Diesel exhaust fluid, or DEF, is injected into the exhaust stream. NOx, traveling in the exhaust, mixes with this exhaust fluid and breaks down into nitrogen and water vapor in the presence of the SCR catalyst. There are three methods of regeneration: passive, active, and forced. Let's review each. Under normal driving conditions, your dashboard warning lights would be off because there is no excess back pressure from the exhaust system. As combustion occurs, it leaves behind particulate matter, which, as mentioned, is typically hydrocarbons from fuel soot and engine oil that is released into the exhaust system. After being oxidized in the DOC, most of the particulate matter is burned away in the DPF, provided the temperature conditions are favorable. This process is called passive regeneration. However, metallic ash from the engine oil remains in the filter and continues to accumulate. Passive regeneration is ongoing and minimally impacts equipment functionality. The hot exhaust dash light may come on during this process. When soot and ash build up in the DPF, the back pressure gauge, or the ECU, triggers an active regeneration. This may happen once or multiple times a day if your work includes excessive idling or stop-and-go operation. The hot exhaust light, or DPF regen light on the dashboard, will alert the driver when an active regeneration occurs. The tachometer will show a slight increase from the added strain an active regeneration puts on engine performance. Fuel efficiency gauges will drop dramatically, caused by the injection of fuel directly into the exhaust system by post-combustion injection, or the seventh injector. The equipment can continue to operate during this process, but active regeneration may also be performed while parked. During active regeneration, the post-combustion injection cycle, or the seventh injector, will automatically spray additional diesel fuel directly into the exhaust system. This will cause substantial losses in real time in average fuel efficiency. The fuel will oxidize in the DOC, adding heat to the DPF. As temperature increases, most of the remaining soot will be oxidized and expelled through the filter. At this stage, the hydrocarbons of the engine oil burn off. However, the metallic components from the engine oil additives are incombustible and remain in the filter-forming ash. Metallic ash will continue to build up because metals cannot be oxidized or burned away. Ash compacts inside the DPF, creating clogging and dramatically increasing back pressure. If adequate exhaust flow cannot be properly maintained through passive and active regeneration, the equipment will need to undergo a forced regeneration. This requires the truck or equipment to be parked with the engine running for up to 1 hour. A blinking DPF regen light and check engine light will alert the driver that a forced regeneration is necessary. The stop engine lamp may also turn on. Once parked, the process will begin. During regeneration, the hot exhaust light will stay on. During forced regeneration, your engine will perform the same operation as during active regeneration. The engine must idle to meet the proper RPM level to activate the regeneration process. The crucial difference between forced and active regeneration, due to the increased clogging of the DPF, is that the equipment must be halted. The engine continues to burn fuel to perform the regeneration as the engine idles, at the expense of average fuel economy and progress on the road or job site. Forced regeneration removes almost all of the remaining soot trapped in the DPF, but once again, metallic ash particles are left behind, continuing to clog the filter. Through multiple cycles of regeneration, more and more metallic ash is left behind. Operating with a clogged DPF causes regeneration cycles to become more frequent. Your engine will also need to work harder, significantly reducing fuel economy. If the DPF becomes more than 80% blocked, the filter is considered fully clogged and must be removed for servicing. Forced regeneration is detrimental to fuel economy, engine performance, and timeliness on the job. It causes the driver to lose valuable work hours while burning excess fuel in the process. This significantly impacts your bottom line and increases the negative impacts on our environment. An illuminated DPF regen light, check engine light, malfunction indicator light, as well as a blinking stop engine light will alert the driver that a DPF service is required. Performing DPF service requires the equipment to be taken to a maintenance shop for extended downtime. Service intervals vary by size, operating conditions, and manufacturer. Servicing a DPF may result in cleaning the unit or completely replacing the filter. Because there is no dashboard gauge to measure particulate levels in a DPF, it is difficult to know when to service them. Many OEMs have resorted to service limits, which can lead to prematurely servicing a DPF that has plenty of life available. Now that you know what is clogging your DPF, you can take action by using the correct engine oil. Using engine oil with low levels of metallic additives will eliminate almost all ash buildup, because 90% of all the ash particles trapped inside the DPF come from additives in the engine lubricant.